Welcome to Lecture 10, Part 1 of Chemistry 312. This lecture is on radiation reactions. It's going to cover dosimetry and hot atom chemistry. The readings for this lecture on radiation reactions can be found in Modern Nuclear Chemistry, Chapters 16 and 17, and Nuclear and Radiochemistry, Chapter 6 and Chapter 11, Point C. The first part of this lecture is going to cover interactions of radiation with matter. We're going to explore the interactions of neutrons, positive ions, electrons, and photons with matter. Lecture 2 is going to cover dosimetry, radiation protection, and hot atom chemistry. The figure here shows an example of what the lecture will cover, where an ionizing particle comes in and creates a free electron and a positive ion. The ionizing particles can be something like an alpha particle, massive, stopped by a piece of paper, a beta particle, the electron, less massive than the alpha particle, and as shown here, stopped by a piece of plastic. And then we can also discuss photons, gamma rays, no mass, requiring material for shielding that's much more massive than either paper or plastic. In a biological system, one can model interactions of radiation with matter through the ionizing effect of particles on water. Fundamentally, in a biological system, water is the most prevalent molecule. Ionizing particles will come in. They can form excited water, hydrogen radicals, hydroxyl radicals, superoxide radicals, or peroxides. All these different radicals have various lifetimes, and through the interaction of the radiation with water, these radicals can then move along a path length and they drive interactions with molecules. This is one of the primary forms of radiation damage. You can also have the particle itself going in and ionizing a molecule. Classic example is when one talks about a particle coming in and cleaving DNA. However, the primary interaction that will occur will be with water, just because there's much more water targets in a biological system than the actual material itself. The interaction of radiation with matter has some commonalities. Ultimately, they lead to dissociation of molecules, excitation of atoms or molecules, and ionization of atoms or molecules. Fortunately, this ionization is easily measured and is used as a means of detecting radiation. There's a commonality in air. About 35 eV of energy are dissipated for each ion paired form. In other gases, this varies a little bit, anywhere from xenon being to close to 20 eV, ammonia 40 eV, and something like helium, which you would expect to be difficult, is on the order of 43 electron volts. Germanium, which is used in gamma detectors, has close to 3 eV. So this radiation, when it comes in, it's detected by the interaction with matter. They ultimately have about the same effect, so 35 electron volts per ion pair formation. So if you measure the total number of ions produced, you can determine the energy of the particle that comes in. Now, how particles interact with matter and how they lose energy, there's some common trends. At high energy, the ion coming in is bare, so imagine a helium nucleus coming in, no electrons, and the energy loss is through electronic excitation and ionization of stopping material. Now, as the velocity of this particle starts to slow and it becomes on the order of the electron velocity in the K-shell of the material that it's traveling through, this ion can start picking up electrons if it's positively charged. So imagine helium starts to become charged. And then as the particle gets slower and the electrons on the valence orbitals, they can start interacting. They have elastic collisions, and this is going to account for some energy loss, and you go from electronic to nuclear stopping. Now, of these three types of energy loss, there's really no sharp differences between point 2 and point 3. These encounters include both elastic and inelastic collisions. So fundamentally, as a particle comes in, there's certain interactions at high energies. As those particles slow down, the energy of the particle starts becoming on the order of the K-shell electron. It starts picking up electrons. Then it starts stopping pretty rapidly. Let's start discussing some of the interactions. First, we'll focus on neutrons. As non-charged particles, they have very little interactions with electrons. Primary ionization is negligible, so you don't expect neutrons to cause a lot of ionization. Their interactions are primarily nuclear effects. So they can scatter. They can have both elastic and inelastic scattering. They can also induce reactions. This is primarily how one would detect neutrons. You can have a neutron coming in, a photon coming out, or a proton, an alpha particle, a number of other neutrons, or fission. So this gave a pretty clear example that a neutron was interacting. So if we then go from neutrons to other charged particles, let's talk about positive ions. So the process for energy loss of positive ions is primarily through the interactions with electrons. You get some velocity of the positive particle that's coming in, and it imparts the electrons is twice this velocity. One can evaluate the velocity from the kinetics. So if you consider something like a 6 MeV alpha to an electron, the average energy loss from one of these ions from an electron is around 100 to 200 electron volts. So an alpha particle comes in, can liberate an electron. This electron can have a good deal of energy, a couple hundred electron volts. That is sufficient to cause secondary ionization. So that ion that's formed, that electron that comes out through the interaction of the alpha particle with that electron, has enough energy for itself to cause ionization. So you get some electron stopping, which is this collision. It's an inelastic collision between bound electrons and the ions. So this can also cause excitation of atomic electrons. And then nuclear stopping, where the velocity of the ion is close to the velocity of the valence electrons, either the K shell or the outer shells. So we described the three different routes earlier. There's the electronic stopping, and then once the ion slows down, we get this nuclear stopping. And the velocity of the ion, when it becomes comparable to the K shell, it can really start picking up electrons, and that ion is passing through the matter. It eventually, it's stripped of all the orbital electrons, whose velocity is less than that ion velocity. So once it starts slowing down, it can really start picking up electrons. The positive ions tend to be much more massive than the electrons. Therefore, they're going to impart a lot of the relatively large amount of energy to that electron, cause those secondary ionization events. But you're also going to have something related to a range, and that's shown in the figure here, where the distance that a positive ion travels is somewhat within narrow limits. It's dependent upon the particle and the energy. And we define it as range, in other words, range of a particle in material. So the large mass, the relative large mass of the ion drives this behavior. This is because you got these fractional energy losses, are relatively small, so you need a large number of collisions to occur before the ion is finally stopped. And the deflection of the ion is relatively small. This is what's called straggling. So imagine a massive particle going through the material. How it gets scattered up or down from a given direction is relatively small. So it tends to go in a path that would be relatively narrow and then deposit a great deal of its energy in a relatively small area. And the figure here shows the number of ions from a point source as a function of distance. So you say the number of alpha particles at a given distance r, it decreases, and the number of alpha particles with ranges that are between r and some plus or minus small amount of r. You see that most of the alpha particles will get deposited for a given energy in a small region. And this is useful if one wants to understand how to deposit certain ions into materials, or if you are using an ion in a therapeutic manner, an external proton source, and you want to have the energy deposited into a tumor. We want to make sure that that tumor location would be where the bulk of the ions are stopped and the bulk of the ionization occurs. So there's a relationship between the positive ion and the range, and it's called stopping power. And it's the change of energy over the change of a distance. We saw that in the range. And this definition of stopping power, it's a function of energy, charge, and the ion mass. And it really talks about some sort of maximum rate of energy loss occurs at low energies. So it's described, one of the ways it's described is what's shown here as a Bragg curve. And this shows the number of specific ionizations as a function of depth or range in a material. You see you have a relatively small amount of ionizations initially. It goes up and then it peaks greatly right near this Bragg peak. And then at a distance beyond that, particles stop, no more ionizations occur. So this energy loss can be described for the distance traveled of a particle. The equations that are used, there are two equations that are listed here, and they include relativistic factors, and the terms include the average fraction of electrons stripped off an ion, the charge of the ion, the absorber, atoms per unit volume, so something about the absorber density, the Z of the absorber, that's important because higher Z material, more electrons, the mass of the electron, the ion velocity, not the electron velocity, and the effective ionization potential. So ionization potentials, different materials, have some different properties on this stopping power. What one can do is evaluate the rates of energy loss for charged particles moving with the same velocity in a given absorber is proportional to the charges. So now if one understands different absorbers, one can understand something about the energy losses because it's just proportional to the charges of a given absorber. So if there's a proton of energy, it would, for deuterium, it'd be twice that energy, tritium 3 times that energy. All would have the same energy loss as a function of distance. And it would be 25% of the alpha at 4 times the energy because of the mass differences. And the fundamental equations describing the energy loss as a function of distance are shown here. And one is for when the velocity is approaching relativistic terms and when it's not relativistic. Now what this amounts to is something that's shown here. One can take that equation and apply it to a given material. So evaluating the stopping power of ions in aluminum. One sees here, one goes from helium all the way down to fermium. So fundamentally the periodic table. This is your range or your stopping power information. And this is the ion energy per unit mass. So it's energy divided by AMU. You can look up this data for particles through all sorts of material, not only pure elements, but mixtures. And what we see here is the rate of energy loss is not the same for different ions with the same energy. So if one examines oxygen 16, 15, nitrogen 14 at 80 MeV in aluminum, we see that we have different stopping powers for these particles. The key takeaway from this is to understand how ions move through material, the properties of the ion, the energy of the ion, and information on the material all come into play. But there are certain trends that are evident. We see that the behavior of the ions shows similar trends, and certainly at very high energies, they all coalesce and have similar behavior through material. So, what's the use of this stopping power information? Well, let's look as an example. Let's talk about a proton stopping in carbon. And what we want to do is we want to calculate some thickness of carbon that's necessary to slow down or stop a proton. This has lots of applications. If I wanted to tune a beam and I knew what the energy was and I wanted to slow it down to a certain amount, I would know how much material to put in front of it. If I wanted to stop a proton from penetrating carbon at all, I would know exactly, depending upon the energy of the proton, how much carbon I should use. So this stopping power is a reasonable estimate. And these equations that we're going to use, they're good for estimates. More detailed equations can be used to really get into the details and get in-depth calculations on how much material is needed. And they do this a lot with medical physics in terms of shielding, or they'll use it in nuclear power plants. So we'll look at the energy loss, which is just the stopping power times the thickness times the density. So we need to determine the stopping power from the particle energy. So what's the carbon thickness to stop a 10 MeV proton? So let's set the loss, right, this energy loss, and solve for the thickness. So we can get data, as shown here. There's a figure that shows the stopping power as a function of energy of a proton in graphite. The graphite density is shown here. There's electronic nuclear total stopping power. We'll just be interested in the total stopping power. This web page is from the NIST site. You can look at stopping power of protons in all sorts of materials. You can have the same thing with alpha particles and electrons in all sorts of materials. So one would set the energy loss and solve for the thickness. We want an energy loss of 10 MeV. We need to get what the stopping power is, and then the density. So the stopping power is 4.084 times 10 to the first MeV centimeter squared per gram. And we get that from this figure. We pulled out the data. This program, this website, allows you to pull out the data specifically. And if we're looking at something on the order of 10 MeV, we see that its stopping power is somewhere right around here. And from a table on the program, it's a little bit harder to see on this figure, but on a table, this is what the stopping power is. We know what the energy loss is. Here's our density. We have 10 MeV divided by the stopping power times the density of the graphite, and our answer is about 1/10 of a centimeter of graphite. If we want to consider uranium with a 10 MeV proton, we can again go to this website. We looked up the uranium stopping power. It's shown here of 1.69 times 10 to the first MeV centimeter squared per gram. The density of uranium is around 19 grams per centimeter cubed. We put this into the equation and we see we need much less uranium to stop the proton than graphite. This figure shows the P-star data, not in the figure form, but from the table. This is what you would see, the density of the carbon, this graphite that was used. There's some selection data on the program. You can download the data. But here you see the kinetic energy, the stopping power, electronic, nuclear, and total. And then something here listed as CSDA, which is the continuous slowing down approximation range. So first of all, the stopping power, as I said from the previous slide, it was pulled out of the table as opposed to the figure. And this was used to calculate the expected range of the proton, 10 MeV proton in graphite. And remember that data was 0.144 centimeters. One can also use this continuous slowing down approximation range, and this is suitable if the particle comes down to rest in the material. So this CSDA is used for an average rest length traveled by the charged particle. You can pull up the data here. You can either use the CSDA or the projected. This is a factor that talks about straggling. So you see that's there's not a lot of straggling. Most of it, 99.81%, does not straggle. So we could use this data here, and I just use the CSDA example here. Take this value. We know the density is 1.7 grams per centimeter cubed. Solve for distance centimeters. We get 0.081 centimeters. And this value is smaller than the stopping power. The stopping power doesn't have as good of an estimation towards the end of the range when most of the energy is being dissipated and most of the reactions are occurring. So for a system where one wants to evaluate an entire range and understands that the particle is going to stop within the material, one may want to use the CSDA. But overall, one should remember that both these values here are really good estimates and gives you an idea of the order of magnitude type thicknesses that are necessary to stop a given particle. Okay, so moving on from positively charged particles, we can go to negatively charged particles, an electron. The energy loss is similar to that of charged particles. Average ionization in air is around 35 electron volts. 70 to 80% of the ionization is secondary for electrons. This has to do with the mass difference. The electron has much less mass than positive ions, so for the same energy, higher velocity, it's lower stopping power. At a maximum of around 150 electron volts, you get close to 6,000 ion pairs per milligrams per centimeter squared. In air, this ionization stops around 12.5 electron volts. So once you get down to that energy, the electrons are going to stop. Electrons can lose a large fraction of their energy in one collision because of the mass differences. And unlike the charged particles that we looked at before, the protons or one with alphas, the straggling is much more pronounced. For electrons, their energy loss is going to occur through interactions with electrons or nuclear scattering. This behavior of electrons, particularly how one could scatter electrons, is actually used in analytical methods. A significant fraction of electrons can be reflected from scattering. And the intensity of this reflection increases with the thickness of a reflector, and you can do this so you can actually achieve a saturation where particles, electrons can be entering material and then scattering back out. So you can get, one can evaluate a ratio of measured activity from a beta source with a reflector to that without a reflector. And this is something called backscattering. So you can understand a backscatter factor. And the factor varies with material, and as one can imagine, the Z, the number of electrons in the material, is going to have an influence on the ability of something to scatter. So one can evaluate a backscatter coefficient and have that reflected against the atomic number, and we can see that lower Z material, lower backscatter coefficient, higher Z material, higher backscatter coefficient. Backscatter is often used in combination with scanning electron microscopy to determine something about the elements that are undergoing microscopic analysis. So again, it's using this fundamental interaction of an electron with material, in this case, in this analytical tool, a unknown material, but by looking at the backscatter coefficient, what percentage of electrons would be scattered back, one can help identify the range of that material. And as we did for the charged particle, we can also look at electron stopping power. In this case, we're going to talk about a loss of energy. Let's imagine that we have a 1 MeV electron that's traveling through 1/10 of a millimeter of uranium. The question is, what is the energy loss of that electron in that material? Well, we can look up the stopping power and understand the thickness of that material times the density. So if we have, we understand what the thickness is, the density, the thickness is 0.01 centimeter. The density is close to 19 grams per centimeter squared. And the stopping power for 1 MeV electron in uranium is listed here as 1.1 MeV centimeter squared per gram. So we plug this into the equation. The energy loss is equal to 0.01 times 1.1 times 18.95. And that's equal to 0.208 MeV. So that's how much energy loss you have. So one would imagine that an electron material, 1 MeV electron, would be able to traverse a 1/10 of a millimeter lead foil and have about 0.8 MeV after passing through it. So if you consider this for graphite, we can do the same thing. We can look up the value for graphite. We see that it's a much smaller energy loss for graphite. Now, one can evaluate, so here is shown the figures for uranium, the figures for graphite. And there's also a specific ionization velocity for electrons and various energies within air. So if you talk about the velocity of the electron, I can either talk about it in terms of energy, MeV, or some fraction of the speed of light. We can see how many ion pairs are made. As we mentioned earlier, at the lowest energy, we get close to a maximum amount of 6,000 or close to 6,000 ion pairs per milligram centimeter squared of air. So we see the same sort of behavior that we saw the range with positively charged particles, where the number of ion pairs that are formed maximizes right as the particle stops. So the electron has the same behavior. Obviously, the difference are charge and primarily the mass. We will close out part 1 looking at the interaction of photons with matter. The photons, unlike the charged particles we were discussing earlier, they lose most of their energy with a few or even a single interaction. However, you need more material for this interaction than electrons or alpha particles. The average specific ionization for a photon is less than that of an electron. However, the average energy loss per ion pair formation is the same at 35 electron volts. Often, one would measure the absorbance of a photon in material. So you could think about it in terms of Beer's law, where you understand an absorbance factor. That gives you an idea of how many photons are actually interacting with material. You can think of this absorbance as one does with UV visible spectroscopy, where you're actually measuring the transmittance. So material or solution that is darker has a higher absorbance, has a lower transmittance. With material, with photon interactions, with matter, you can have the same sort of effect where you talk about a thickness of a given material and what percentage of photons will be absorbed by that thickness of material. And the interactions of photons with matter occur through three main routes. One is the photoelectric effect, Einstein, famous for the photoelectric effect. It basically says a photon with a given energy ejects an electron and imparts an energy on that electron that's equal to the photon energy minus the electron binding energy. This is a tool that has been used to measure binding energies. Most of the electrons that get ejected are the K-shell electron. There's some L-shell electron. There's obviously proportionality between electrons and the absorber. So the proportionality is actually Z to the fifth for this absorber. And for 5% photoelectric effect, gamma energy needed for different materials varies. As we see for aluminum, it's a relatively low amount, and for lead, it's a higher amount. So this photoelectric effect is competing with other effects for the interaction of the photons with the matter. But we certainly see that from this effect, the gamma energy needed for different Z's, we see that there's a relationship and a difference between the material and the behavior. So aluminum, don't need much photon energy. Lead, you need a lot. This is also one of the reasons, or an observation, that thicker material, denser material is better shielding for photons. There's two other effects. One is the Compton effect, as opposed to the photoelectric effect. The Compton effect, where the photon just loses part of its energy to an electron. The photon is scattered. And there's an equation that describes the minimum for scattered, minimum photon energy from something that's scattered is shown here. It's just equal to 1 divided by 1 plus the energy times twice the photon energy, where this electron rest energy is the E naught. So you can see a backscattered peak on a spectrum. You can see the photon coming out. You can have scattered. You can have this Compton effect, which is when you do gamma spectroscopy. You can observe the this Compton effect peak. You can also see the Compton background. A final reaction is pair production, where a photon comes in and it has enough energy to produce an electron and a positron. It's proportional to the energy and the square of the material in which the reaction is occurring. And obviously, it's more common at high energy. You need at least 1 MeV photon for this to occur, because you have to create both the positron and electron. This obviously higher energy route is something that is less common with a photon that's produced through gamma decay. Now, the variation of the Compton photoelectric effect and pair production with different materials is observed here. We have examples for aluminum, copper, and lead. And what's plotted is the cross-section as a function of photon energy. And some of the commonalities, you see that pair production goes up as photon energy increases, having only, it needs to be above 1.1 MeV, but really you only start observing it in a real, measurable amount above 2 MeV. And we do see that the amount of Compton scattering dominates for a range from about 0.5 to 3 MeV for all the materials. And for the lighter materials, Compton is the main and primary interaction. As we see for aluminum, the Compton effect is the primary interaction of photons with aluminum. However, those cross sections, as you see, are around 6 barns, whereas for copper, the cross section goes up to on the order of 20 barns, and for lead, the cross section for Compton's at 40 barns, whereas for the photoelectric effect, the cross section is massive, well over 200 for energies below 0.2 MeV. So from this, one can observe that the higher the Z, the greater the interaction of photons with that matter, and also the variety of interactions vary, with lead having large photoelectric interactions anywhere below half an MeV. For copper, that's around 0.2 MeV, and for aluminum, Compton is the dominant interacting reaction over all the energies examined. One can also discuss the gamma attenuation. As we said earlier, you can model the interaction of photons with matter as one does with UV visible spectroscopy using Beer's law. We have an equation that says the intensity of the photon's final is equal to the intensity initial e to the minus a mass attenuation coefficient times the thickness of the material times its density. This equation is very much similar to decay equations as we discussed. So if one has the mass attenuation coefficient, a material thickness, and density, one can calculate the attenuation of photons through that material. Similar to decays, one can also calculate a half thickness, similar to half-life. So for a given energy, if you're given the mass attenuation coefficient, you should be able to set the photon final or photon initial to 1/2 and solve for the thickness that's responsible for cutting down the photon intensity by 1/2. And one could use this as a rule of thumb to talk about if one has a photon, for instance, a photon for something like thallium-208, which is a 2.6 MeV photon that's responsible for a large dose. If you had the half thickness, you'd know how much material you would need to cut down the dose by 1/2, by a quarter, to a quarter of the amount, to 1/8 of the amount. So as a simple example, one can determine what fraction of 2 MeV photons that pass through 5 centimeters of lead at, what's the fraction of those photons that survive. One can go to, again, the NIST database, look at some mass X-ray mass attenuation coefficients for 2 MeV photons. The value is shown here. One plugs this into the equation where the amount that passes through, the intensity final by the intensity initial, is equal to e to the minus the mass attenuation coefficient times, we said, 5 centimeters of lead times the density of lead, and it equals to about 7.3% of the photons pass through that lead. This concludes part 1 of the lecture on radiation reactions, dosimetry, and hot atom chemistry. When you've completed this lecture, please go to Part 2, where we'll discuss dosimetry, radiation protection, and hot atom chemistry.